Good afternoon, everybody. Happy Monday. Good to see you. Time to start lecture. So let's start off with a survey question from last time. Actually, there's a couple of survey questions on this one. The first one has to do with multi-step synthesis. So this is one of the things we ended up with in the last lecture, talking about planning a multi-step synthesis. And so here's the question. It's how could you take benzene, the material on the left there, and make this substrate out of it, where you have a benzene that now has a tert-butyl group, and then across the ring from it in the para position is an NH2 group. And there's 4 different options, A, B, C, D, E. And so what I'm going to do is go through the solution with you, but not just the solution, but what happens in every single one of these instances. So at the end of this question, if you submit it, once you submit it, you get the feedback that's shown here. And what happens with the first couple of options are what happens if you do option A or C. So if you lead with nitration with HNO3 and H2SO4, you get nitrobenzene. But then all your efforts to put a carbon group on via Friedel-Crafts alkylation would fail because this reaction doesn't work with strongly deactivated rings. So don't start with a strongly deactivated ring. It doesn't matter what you would try to do in the next step. I mean, you could reduce this to an NH2, but that would still be a problem. So let's take a look at what happens in some of these other scenarios. Option B is actually the one that works. If you start with benzene and then you first put your carbon group on with Friedel-Crafts alkylation using tert-butyl chloride and aluminum chloride, you get a tert-butyl group on the ring. That'd be a mono-substituted product that reaction would work well. Then if you nitrate in the next step, this is an ortho-para director, so the substitution would want to happen ortho and para. And due to the size of the tert-butyl group, para is a really good option. So this would be a good way to make this substrate. And then the last thing you would do, it'd be to reduce the nitro group using one of the 3 reducing conditions that we talked about last time. This is one of those 3 options, hydrogen, palladium on carbon. You could also use tin and HCl or iron 0 and HCl, so metallic species to donate electrons and HCl to provide H's. That would get you the product. The other scenario, which is option D, wouldn't work for a different reason. So if you first nitrate, you get the nitrobenzene, and then you reduce it with hydrogen, palladium on carbon, you do get this aminobenzene, aniline. However, if you try to do the Friedel-Crafts alkylation on an aniline, remember this is another limitation of Friedel-Crafts reactions, is they don't work with anilines because the aniline lone pair on the nitrogen likes to complex to the aluminum, and that basically stops the reaction from happening. Nothing else happens after that. So this is a dead end as well. So option B. And when I looked at the statistics for this one, most people got it, or that was the plurality of the students got it. More people than not selected B. There were a bunch of other options as well that people selected, but this was the most popular one, so that was good. The next question on that survey dealt with the reactivity of aldehydes and ketones. And this one, actually, a lot of people got this one right too, which I was a little bit surprised about because we hadn't quite gotten to this last time. So here's what's going on here. Order of reactivity for aldehydes and ketones depends on 2 things. How congested is it at the carbonyl carbon? In other words, how easy is it for a nucleophile to attack the partially positive carbon there, or there, or there, or there? So there's a steric hindrance aspect to it. That's like factor number 1. Factor number 2 is how electron poor is the carbonyl. Every one of these C double bond O's is electron poor. It's got an oxygen that's doubly bonded to it that pulls electron density towards it. So each of these develops a partial positive charge, but they're not all the same. And so what I want to do before I talk about the solution to this one is just talk about this feature over on the board over here. So let's chat about what makes an aldehyde or ketone more or less reactive. So I'm going to say here in this section that aldehydes are generally more reactive with nucleophiles than ketones. And there are two reasons. Okay, so reason number one has got to do with the steric hindrance argument. So if you have an aldehyde, for example, I'll draw that over here. You've got a hydrogen on one side and an R group on the other side with a ketone. You've got a situation where you've got R groups on each side. The R groups in the ketone could be the same or they might be different. But in all cases, the R is going to be way bigger than the hydrogen. So a hydrogen is a very small atom, just because it's only got one proton, it's really tiny. Compared to any R group, which is going to go from large to extra large. Right? And if you look at a ketone, ketone's basically got two of these big bulky groups. That's going to make it hard for a nucleophile to approach the carbonyl carbon. So issue number one is steric hindrance. In ketones is greater. So that's an issue. If you're a nucleophile and you're trying to attack a partially positive carbon, you're going to have a harder time with a ketone. Reason number two is that alkyl groups donate electron density into the C double bond O carbon. So these R groups, they have a tendency to push a little bit of electron density in to make that carbon a little less partially positive. Aldehyde has one of these R groups, ketone has two. So that makes ketones less reactive. Therefore, ketone C double bond O carbon is less positive. They both have partial positive charges, but the partial positive charge is bigger on an aldehyde than it is a ketone. So if you're a nucleophile and you're looking at these two carbonyls, this one is less attractive because it's less partially positive. There's a stronger attractive force to this one because it's more positive. So that's why aldehydes, and just to make sure we're clear about this, this is the aldehyde, and this is the ketone. All right, so that's the reason. So let's go take a look with this in mind at this survey question and talk about the differences. So the survey question has one ketone and 1, 2, 3 aldehydes. So the ketone is going to be the least reactive because it's sterically the most hindered and it's got the least the least partially positive carbonyl group. But these three aldehydes are different. So let's think about them in terms of like, what is their steric difference? Well, this one has an isopropyl group next door. That's the biggest R group. This one has a carbon and a fluorine, and fluorine is about the size of like a methyl group, I would say, or maybe a little smaller. But then there's ethyl. So basically, this one's got a bigger group. These have smaller groups. Between these, the fluorine has a powerful electron withdrawing effect. So it tends to make this carbonyl really partially positive. So this is going to be the most reactive of the carbonyls up here because it's got minimal steric hindrance and it has this really strong partial positive charge there. So this is the most reactive. And then this would be the next most reactive because it's just got kind of one R group, but not a lot of steric strain hindrance there. Whereas this one has an R group, but significantly more steric strain. So most reactive, second most reactive, less reactive, least reactive. So the answer is most reactive is 2, least reactive is 4. This is the correct one, C, and most people got it. I mean, not everybody, but that was, I think your instincts are good if you selected C. Any questions about this? All right, I want to go through that question that I left you with on Friday. So there's one more multi-step synthesis question that we're going to chat about here. And that was, how do you make a benzene with 3 different groups on it, starting from benzene, and setting up your synthesis scheme in a way that gets the substituents on the ring and in the right places. So here was the question. How do you take benzene and through a series of steps, this double arrow here is just saying it's going to take a bunch of steps. And I'm going to say, I'll do that to indicate there's going to be 4 steps. That is the simplest way that I can think of to do it. With the reactions we know, and generate this species where you've got an alkyl group on one side of the ring, an acyl group on the other, and a nitro group in this spot right here. So it's probably a good idea to think about what kinds of conditions do you need to install these different groups. So for example, this one has to go on via Friedel-Crafts acylation. This one goes on via nitration. HNO3, H2SO4. This has got to go on via one of the Friedel-Crafts reactions. The problem is if you try to do Friedel-Crafts alkylation to put this group on, you get a rearrangement. You get a tert-butyl group on the ring instead of an isobutyl group, which is what we need. So this is one of those that if you try to use Friedel-Crafts alkylation, you're going to have a problem. And so what you need to do here is you need to first do Friedel-Crafts acylation to put the carbon group on. And at that point, there'll be a C double bond O at that position. And then you have to reduce it. So those are the 4 steps that you're going to need. And getting them in the right order is the trick. So here's a general tip that you can use for solving these kinds of questions. If you've got carbon groups to put on your ring, that's going to be Friedel-Crafts alkylation, acylation type reactions. If you need to do those reactions, do your other reactions to install electron withdrawing groups later. Put the carbon groups on first, because if you put a nitro group on first, for example, it's going to kill all of your Friedel-Crafts reactions because they don't work with strongly deactivated rings. So we have 2 carbon groups we need to put on. A Friedel-Crafts acylation to put this group on, and then an acylation and a reduction. If you put this group on, it would, by Friedel-Crafts acylation, you can't put any more carbon groups on because it's a strong deactivating group. So this group really needs to go on first. First we need to Friedel-Crafts acylate, and then we need to reduce. So let's work on that. So if in the first step you do Friedel-Crafts acylation by using this acid chloride and aluminum chloride as your Lewis acid, you get this species, which has the makings of the substituent in the upper right-hand corner. It's not quite there yet, but we're going to need to reduce this to get the alkyl group to go forward, because if we left this as is, the Friedel-Crafts reaction to install the other alkyl group wouldn't work, and if we tried to nitrate it, the nitration would go on the wrong spot. So there's just all kinds of things that are wrong about this substituent as it is. But if we were to reduce it using either one of the 2 methods, zinc, mercury, the amalgam, and HCl, that would do it. Or if you prefer, you could do the Wolff-Kirschner reduction, where you use this hydrazine reagent and hydroxide. And either one of those would give the alkyl group. It reduces the carbonyl, carbon, to give you an alkyl group. And now we're set up for success in the rest of the reactions because we've got an ortho-para director here. So we could do probably, the next thing you would have to do would be your Friedel-Crafts acylation reaction, because if you nitrated, you get the nitro group on the ring in ortho or para positions, but then there's some question as to whether the next Friedel-Crafts reaction would work. So what you should do next is Friedel-Crafts alkylation to put this group there. And Friedel-Crafts reactions tend to be, a lot of times they're pretty selective for para substitution. So you would probably also get some of the ortho, which would be a product you would have to separate, but at least the desired product would be a major product. And now this is actually set up perfectly to put a nitro group in the right spot, because it's doubly activating, or doubly selecting, I shouldn't say doubly activating, doubly selecting for these positions right here. This is an ortho-para director, which is putting partially negative charge in these spots, and this is a strong electron withdrawing group that's putting partial positive charges on the positions that are ortho to it. So both groups are directing to these spots, and when you nitrate it, in the last step, HNO3, H2SO4, the nitro group goes in the right spot. So these are all the things you want to be thinking about when you're planning the synthesis. And if you get any of the steps in the wrong order, something's going to go wrong. And with these questions, sometimes there's more than one correct solution. Sometimes there's one really correct solution and one solution that'll work sort of well, but not as well as another. And it just kind of depends on the molecule. So I'll select ones where there's a good path to get from starting material to product. And I won't pick anything that's like ambiguous or impossible to synthesize well using the reactions and theory So, all right, so let's go back to talk about carbonyl chemistry, introduction to carbonyl chemistry. All right, we were talking about aldehydes and ketones, and we're going to talk about their reactivity now. So we've got reactions of aldehydes and ketones is the next thing that we're going to cover. A whole bunch of reduction conditions. We're going to talk about all of these. I know the font is really small and there's a lot of information in this slide, but you're going to get this on an exam. So while you're studying, look at this thing and just get familiar with it, because it's kind of like the best note card I could think of. If I was going to put all the reducing reactions and reagents down from this chapter into a condensed format that I would want to have on an exam, this is what I did. It lists every reduction reaction you're going to look at and every reagent you're going to see. You just have to get used to it. So we're going to talk about them one by one here, and the first ones we're going to start with is ours with this top one, which is hydrogen palladium on carbon. It adds hydrogen across double bonds in a process called catalytic hydrogenation. We looked at this in chapter 12 when we were looking at reduction reactions. So we learned about how carbon-carbon double bonds will react with hydrogen and palladium on carbon, and you can add hydrogen across carbon-carbon double bonds. And that's what's happening in this step. So this is a molecule that's got two different functional groups in it, a C double bond O and a CC double bond. And so what this is saying is that if you put hydrogen in and palladium on carbon, just like we learned earlier in the semester, it'll add across that bond and give you a new molecule that's reduced. So adds across the carbon-carbon double bond. And that's a fast reaction. Now, one of the things that's new for this chapter is that reaction works with C double bond O as well. So it likes to add also across the C double bond O, adding hydrogen to each one of those atoms to give this species. But the thing is that's a lot slower. So the reaction is fast with carbon-carbon double bonds, slow with carbon-oxygen double bonds. And that's what this box is summarizing in words. It says reduces C double bond C rapidly, reduces C double bond O slowly, can be used to reduce C double bond C in the presence of C double bond O. So like say, for example, you just wanted to reduce the carbon-carbon double bond here. All you need to do is do this reaction, limit it to one equivalent of hydrogen. In other words, stoichiometrically, only give the reaction one equivalent of this per every one equivalent of this. Equal moles of these things, and the CC double bond will get reduced before that anything happens over here. If you want them both reduced, you just add excess hydrogen and you let it go a long time. So that's a way to reduce C double bond O. All right, the next one we're going to look at is using a reagent called sodium borohydride, NaBH4. that is a mild source of the nucleophile H-. So I want to talk about this reagent, which I've shown here in red, over there on the board. We're going to talk about it, and then we're going to come back here. There are two hydride sources that we are going to talk about in this chapter, and I'm going to introduce them both right over here. One of them is this sodium borohydride. The other one is lithium aluminum hydride. We've seen the lithium aluminum hydride before, but this is the first time I think that we've seen sodium borohydride. So these are what are called metal hydride reagents. They are sources of H with a lone pair and a minus charge. That is a strong nucleophile. We're used to seeing hydrogen with a plus charge on it. That's called proton. This is a completely different animal right here. Having two lone pairs and a formal negative charge just turns its behavior completely 180 degrees. This is now a strong nucleophile. It's also a strong base. It likes to attack positively charged things. So these are the two reagents that we're going to work with. The first one is the sodium borohydride reagent. So I'll draw it up here. It's a central boron that's got 4 H's attached and a formal minus charge. Then there's a sodium counterion that goes along with it. And this is a mild source of H- hydride. It is got this Lewis structure. You'll see it written out sometimes as by its formula NaBH4. A lot of times over a reaction arrow. That'll be shown because it's a lot more compact and easy to fit on a piece of paper. You might also see it listed as its full name, which is sodium borohydride. And the reason it's a hydride source is because of the electronegativity difference between boron and hydrogen. So one of the things we said about electronegativities is that hydrogen and carbon are pretty much the same. They're very, very similar. Well, if you look at the periodic table, which is way over here, boron sits to the left of carbon. So boron is less electronegative than carbon, which means it's also less electronegative than hydrogen, which means that the polarization here is that these H's have a partial negative charge. They're hydride-like, hydridic in nature. So even though boron has a formal minus charge, these H's have a lot of negative character. They like to take the pair of bonding electrons and go and run with them and attack something positive like a C double bond O carbon. So we're going to see them doing that. We're going to see them taking a pair of electrons, leaving boron, and going and attacking a partially positive charged carbon. So that's mild source of H-. Now take a look at this one. This is one that's structurally very analogous. It has a different atom in the middle. It's an aluminum instead of a boron. And we've got, instead of a sodium, there's a lithium, but that isn't a big deal. This is called a lithium aluminum hydride. It has the formula LiAlH4, and it's called lithium aluminum hydride. And it is a powerful source of H-. The reason is that, again, there's an electronegativity difference between hydrogen and aluminum. But since aluminum aluminum and boron are in the same group, So when you look at the periodic table over there, group 3, boron is on top, aluminum sits right below it. So they have a lot of similar behaviors. But aluminum's less electronegative, so there's a bigger difference here. So these hydrogens have bigger partial negative charges. They're sort of more aggressive H- sources, and this is a really powerful source of H-. Between the two, if you drop this one into water, it'll fizz and generate hydrogen gas. This one will react very violently. It'll release hydrogen gas. It'll catch on fire. So it generates. I mean, it's just qualitative way of showing that they're really different in terms of their intensity. They do the same thing, but to a more aggressive extent over here and a milder extent over there. So we're going to see both of these reacting with carbonyl in a bunch of different contexts. So let's head over here and take a look at this chart that I've got for you. And with this in mind, let's look at sodium borohydride. So sodium borohydride, NaBH4, sodium borohydride, a mild source of the nucleophile H-. If you start with a aldehyde or ketone, which is shown as a carbonyl here with an R group on one side, and then on the other side bonded to the C double bond O is either a hydrogen, which would be an aldehyde, or an R group, which would make it a ketone. So either aldehyde or ketone reacts with sodium borohydride. One of the H's comes over and attacks that carbon, adds to it. The electrons go up onto oxygen, and they pick up a proton from an alcohol, which is the solvent, to give this product, which is a reduced carbonyl. That carbon used to be a C double bond O, having 2 bonds to oxygen and no bonds to hydrogen. And then in the product here, it's got 1 bond to oxygen and 1 bond to hydrogen. So it's clearly undergone a reduction. Hydride adds once to it. And we're going to look at a mechanism for this. But the thing about this reagent is you'll only see it in this chapter used in one context, and that's only used to reduce aldehydes and ketones to alcohols. It's too weak to reduce other C double bond O compounds, or the reaction's complicated. It's basically, it just gets used for this one job. So you see this is one reaction that it's shown with here. Lithium aluminum hydride is a lot more powerful reagent. So LiAlH4, lithium aluminum hydride, is a powerful source of the nucleophile H-. And it gets used in a lot of different reactions. One thing that it does is it will reduce aldehydes or ketones. That's what's shown here. Carbon bonded to carbonyl, and then on the other side of this carbon bonded to the carbonyl, either an H or an R, that's aldehyde or ketone. It reacts with lithium aluminum hydride followed by treatment with water to give an alcohol. So the result is almost exactly the same as up here. It is exactly the same as up here. It's just this is a 2-step process, and we'll talk about why that is here in a minute. The thing about this is it'll reduce a whole bunch of other reagents too. So if you've got other carbonyl compounds that are like esters, carboxylic acids, and hydrides, acid chlorides, it reduces them too, but it gives something that's a little different, and we're going to talk about this later. It turns out it reduces them, adds hydride twice. We'll go through the mechanism and explain why that is. It also reduces amides, which is another class of carbonyl-containing molecules, to amines. Hydride adds twice. So we're going to dig into this lithium aluminum hydride reaction, like its reactivity, pretty deeply. But for right now, with aldehydes and ketones, we're going to focus on this first box, this first reaction, and talk about that. And basically, the bottom line is lithium aluminum hydride reduces every carbonyl group it comes across. Every C double bond O it sees, it reduces. It adds H- to it. Water is added as a proton source in the second step. Okay, so this covers the reactivity of aldehydes and ketones. This page right here, these 3 reactions. And so what I'm going to do now is go through the mechanisms of these metal hydride reductions to show you how they work, and then we'll do a little bit more with this, and then we'll talk about some reductions of other carbonyl groups. But do you have any questions so far? Like, we're just kind of getting started with these reagents, but all right, let's talk about mechanism. So aldehydes and ketones have a reactive C double bond O. Carbon. That carbon is reactive with strong nucleophiles. So here's how it works with the lithium or with the sodium borohydride reaction. So I'm going to show an aldehyde or a ketone here, and just remind you that that carbon is partially positive, and sodium borohydride with its partially negative hydrogens is attracted there. So the electrons in this hydrogen-boron bond, they go to attack that carbon, make a new bond to it. This oxygen has 2 lone pairs, and what I'm saying with this arrow is it's going to get another one. And we're going to get an intermediate that looks like this. We have an O minus. We've just added, this is the group that was there before. It's either an aldehyde or a ketone. And then this is the new H that we added from the sodium borohydride. Maybe what I should do, and I can do this while we're just learning this, is put it in a different color. I'll make sodium borohydride orange, just so you can keep track of where the hydrogens are coming from. And there's a sodium up here. That's the counter ion. I'll make the sodium orange as well because it came in as the same reagent, sodium borohydride. So there's a sodium cation up here. All right, so that's the reduction event. The hydrogen from the sodium borohydride attacks the carbonyl, makes a new bond to it. We've got a reduced species. The other thing about these reactions is they're always done in an alcohol solvent. You'll see most often methanol as the solvent, but it could be ethanol, it could be other alcohols as well. But the reason this is in there is that it's a source of proton that this O minus can use to grab to get a proton to become neutral. And that's what happens in the next step, is that the solvent supplies a proton to this O minus. So the O minus goes and grabs a proton off of the solvent, and you get this alcohol product and then this OCH3O minus, that's going to end up sticking to the boron. And so what ends up happening is the boron ends up with an OCH3 attached in addition to these other H's. And these H's can continue to react potentially. So the boron still has 3 H's attached. So it can go on and continue to react 3 more times. But that's the product we're looking for. That's the alcohol. So this is an alcohol product. And whether you start with an aldehyde or ketone determines what kind of alcohol it's going to be. If it was an aldehyde that we started with, we'd have one R group, and it would be a primary alcohol. If it were a ketone that we started with, it would be a secondary alcohol. So primary or secondary alcohols are going to be the products of this reaction. All right, that's sodium borohydride reduction. Let's talk about the lithium aluminum hydride reduction, which is got real strong parallels. It's very similar. The only difference really is that you can't have the proton source solvent and the reducing agent together with lithium aluminum hydride, because lithium aluminum hydride is just too aggressive. If you were to stick lithium aluminum hydride in here, the H minuses would just grab the proton off of the solvent, and the reagent would immediately quench itself. It would no longer be lithium aluminum hydride. This is mild enough that it'll coexist with the solvent long enough for you to get the reaction done. So that's the thing about this. It's mild, so it tolerates being present with a protic solvent for a little while. Okay, let's talk about lithium aluminum hydride reductions. So lithium aluminum hydride reduction of aldehyde and ketone is very similar. Just going to do a little better job erasing this board. And then go through it. So if you start with an aldehyde or ketone over here, like we did over there on the other board, with this diagram, I'm saying it's a carbonyl with an R group, and then on the other bonded group to the carbonyl, it could be either an H or an R, so either aldehyde or ketone. If you put this in with lithium aluminum hydride in the first step, LiAlH4, and then in a second step, treat it with water. And I think what I'll do here again is use the orange on this reducing agent to just indicate where the various hydrogens are coming from. We'll get out a product. Let's go through the mechanism here and see where we end up. So with lithium aluminum hydride, it's a powerful source of H-. So the H's on this aluminum are hydridic. They're hydride-like. They're very strongly partially negative. There's the lithium counterion. So they're going to come up. Oh, I need to make this orange. Or I want to make it orange, I say, just for demonstration purposes, so we can keep track of which hydrogens come from where. Because the carbonyl carbon has partial positive charge, electrons in the aluminum hydrogen bond are mostly on hydrogen. The hydrogen, one of the hydrogens will take them and go and attack the carbonyl to make a new bond between carbon and hydrogen. And so what you get out of this then is a molecule that now has an O-. We added a new hydrogen to this from the reducing agent. And then the other group that was there is still there. It's still either hydrogen or carbon group. And there's a lithium counterion here. And that's where it sits until you add H2O. So the point of the H2O is to provide a proton for this O-. In the other mechanism, the sodium borohydride reduction, it was the solvent that did that. But here we can't use water or alcohol as a solvent. It's got to be some aprotic solvent to be able to tolerate lithium aluminum hydride. But what happens in the second step is then the oxygen, the O-, grabs a proton off of the water, and you end up getting this species where we've got an alcohol, just like before. This is an alcohol product. It'll either be a primary or secondary alcohol, depending on whether you started with an aldehyde or ketone. If you start with an aldehyde, you get a primary alcohol. If you start with a ketone, you get a secondary. So it just depends on what the starting material is. All right, so with this then, we've got a couple of different methods to, well, 3 different methods to reduce aldehydes and ketones. We've got hydrogen, palladium on carbon, catalytic hydrogenation, that's one. Then we've also got reduction with sodium borohydride, and then we've also got reduction with lithium aluminum hydride. So we got 3 different ways to reduce C double bond O. And let me show you a way in which you can selectively reduce different functional groups in a multifunctional molecule using these 3 different techniques. So here is I'm just going to put this carbonyl group in a little bit different spot. It'll give me a little bit more vertical space. All right, this is one, there was an example of this that turned up in the chart that I gave you. All right, what happens if you reduce this with one of those metal hydride reducing agents? So if you use sodium borohydride and methanol, or you use a 2-step process where you use lithium aluminum hydride followed by water, both of these are going to give you the same thing. We're going to reduce the C double bond O carbon. We're going to get a hydride that's going to add there. But the double bond is going to be left alone. So this is a way to reduce selectively a carbonyl group in the presence of a C-C double bond. Because these metal hydrides only attack the partial positive charge on the carbonyl carbon. All right, what if you want to reduce just the C double bond C? If you use palladium on carbon, metal catalyst, and then hydrogen 1 equivalent, hydrogen has the ability to add across both bonds, but it's much faster with CC double bonds. So that's the reaction that's going to happen first. And if we limit it to 1 equivalent, just the carbon-carbon double bond will get reduced. So we'll keep the C double bond C, but we'll end up with a couple of new hydrogens that have been added specifically, exclusively to the carbon-carbon double bond. These H's here are coming from hydrogen in the hydrogen palladium on carbon. Up here, that H is coming from either lithium aluminum hydrides, H's, or the H's on sodium borohydride. And then finally, if you want to reduce everything, you could either do both of these reactions, or if you wanted to do it in one step, use palladium on carbon, let's make it orange to begin with here, H2 in excess. And just let the reaction go until both double bonds get reduced. And in that case, you would get both an alcohol and the alkene portion getting reduced to an alkane. And I should make this an orange hydrogen as well, just because that one also comes from the hydrogen. So depending on what you want to do, what do you want to reduce? You pick one of the 3 different options that we've got, and you can get that job done selectively. So there'll be practice with this in the homework, trying to get used to that and comfortable with it. All right. Any questions about this? Yes.
Why doesn't the hydrogen go to the oxygen first?
Oh, are you talking about in this reaction?
No, the middle reaction.
The middle reaction. Why doesn't it go? Okay, because there's different rates. So the question is why does it leave this alone and attack here? It's just because it's able to react a lot faster with carbon-carbon double bonds. So it's just a matter of rates. It will reduce this one and that one. But this one goes so much faster that basically this one reacts first, and then after that, if there's any leftover hydrogen, it'll start reacting here as well. But if we limit it to one equivalent, if we only have 1 mole of hydrogen per mole of substrate, it's pretty selective for just reducing the carbon-carbon double bond. All right. Let's talk about stereochemistry of carbonyl reduction. So this is another thing, is that some of these reactions are producing stereogenic centers, and I've kind of glossed it over here. Haven't really paid much attention, but if you're watching, there's a new stereogenic center that developed there. So this would actually be a mixture of 2 stereoisomers. 2 stereoisomers form because we made a new stereogenic center. And so this is one of the things to keep track of when you're doing reductions with aldehydes and ketones, especially with ketones, because they're the ones that are going to give secondary alcohols which can have stereochemistry. So let's just go through a couple of examples over here to get comfortable with that and make sure that you're watching for it as you predict products. So this is about stereochemistry. Of C double bond O reduction. And what I'll say is when a new stereogenic center forms, stereoisomers result. Because the stereogenic center, with these reagents, there's no way to select which stereoisomer gets formed. And let me show you the result here with a pretty simple example. So this is a really quite simple ketone. It's 4-carbon ketone. But we've got an ethyl group on one side and a methyl group on the other side and an oxygen. If we add a new H to this carbon right here, we're going to generate a carbon that has 4 different groups. That's a stereogenic center, and it's going to be chiral. And when, like, say, for example, you use sodium borohydride, if you use this reagent, NaBH4 and CH3OH is the solvent, we're going to get a new H there. And so the connectivity is going to look like this. We're going to have an OH there and an H here, but that's a stereogenic center. So the H minus can't distinguish between the top face and the bottom face, from the face closest to you or the face furthest away. And so both of them are going to be reactive. So some of the time it's going to come in, the H minus is going to come in from the side closest to you. So it's going to come in with a wedge bond orientation, and this H is going to be on a wedge bond. And the OH is going to get pushed into the plane of the board and be on a dash. The other thing you might get is the other stereochemistry where it comes in from the backside, in which case then the H is going to have a dash bond orientation and the OH will be on the wedge. So the big thing is just not to forget about that and make sure that you're just looking for stereogenic centers forming and then drawing both options. Okay. We're going to change now to looking at the reductions of other carbonyl groups. So we're going to discuss reductions of these other carbonyl derivatives that are like this. And this is going to include molecules like esters, carboxylic acids, and hydrides, acid chlorides, and amides. So there's a lot of different species that can be reduced, that are derivatives that have this general formula that are reducible, that will find ways to reduce. The results are a bit different though because they contain a leaving group. In these reactions, the Z group acts as a leaving group. And the results are a bit different depending on which of the derivatives you are working with, whether it's an ester, carboxylic acid, anhydride, acid chloride, or amide. But that is one thing that is the same in all of them, is that when a hydride adds to the carbon, this Z ends up being a leaving group and leaving. And so now we're going to take a look at a bunch of different types of these derivatives to figure out how they work and which ones do what. So I'm going to bring my chart up again and talk about the next one on the list. All right, so let's scroll down and talk about lithium aluminum hydride, which is this powerful source of H-. So I'm in this line right now. We talked about how it does this. Now we're going to talk about how it does this. So here is that carbonyl with a Z group, and the Z can either equal OR, OH, the anhydride carboxylate group, or chloride. These all behave the same way in that lithium aluminum hydride adds hydride twice. So if you take a look at the carbonyl group here, and then you look at the product, there are two red H's attached there, meaning it got two equivalents of H-. And whether it's this or this or this or this, the results are the same. The one that's different, the only one that's different, is amide is a little different. Hydride adds twice there, but the nitrogen doesn't function as a leaving group exactly. It's the O that functions as a leaving group. So amides are a bit of an exception. So what we're going to do now is talk about these and describe how they work. Okay, let's chat about lithium aluminum hydride of acid chlorides and esters. Lithium aluminum hydride reductions of, we'll look specifically at esters and acid chlorides because they're very similar in terms of their mechanism. And here's mechanistically how it goes. I'll start off with acid chloride because acid chloride is the most reactive of the bunch. And the way that this reaction would be posed is it would be, in the first step, you'd be treating this with lithium aluminum hydride, and then in the second step, you'd be treating it with water. And what you would assume here is that there's excess lithium aluminum hydride, enough H's to react as many times here as is possible with this, because the reaction adds two H's, but you can't stop at just one. So it's not possible to just run this reaction halfway. So people don't try. They add an excess of this, and the reaction then goes to give one product. So here's how it works. Lithium aluminum hydride is this powerful source of H-, and it's attracted to the carbonyl carbon of this acid chloride because it's a really electron poor carbon. So what happens is the partially negative hydrogen goes up and makes a bond here, and electrons get pushed up onto the oxygen of the carbonyl. And what that gives you is an intermediate that looks like this, where we've got an O-, we have the chlorine still attached, and we've added a new H. That came from the lithium aluminum hydride. And with aldehyde and ketone reductions, that's a stable intermediate because aldehyde and ketone don't contain a good leaving group. But here, chlorine is a good leaving group. So what happens really quickly is that pair of electrons on this O swing back down to reform the C double bond O, and chloride gets bumped out as a leaving group. So this is a type of mechanism called an addition-elimination reaction. So I'm going to introduce that to you here. This first step is an addition reaction because we're adding a hydride. The second step is an elimination reaction because we're kicking out a leaving group, chlorine, and that gives the following species. Now we have, look at that, we have an aldehyde. And the thing is we know what aldehydes do with lithium aluminum hydride. They react again. So this is how you get the two equivalents. Is that the intermediate species here is an aldehyde, which is a reactive carbonyl. And so electrons in one of the H atoms, because it's partially negative, likes to go and attack here. And you get a new intermediate that looks like this, where we've got a second hydrogen that's added. We've added two hydrides now. One from the first addition, one from the second addition. There's a lithium cation here. And then the last step is the water addition. So that is just where water provides a proton to that O-. So O- goes and grabs H off of water, and then you get to this final product, which has the carbonyl group has now become a primary alcohol. So this is the product. Two H's add. So we'll talk more about this mechanism, how it works with esters when we come back next time. And then we'll look at some other specialty reagents that have the talent that they can stop at one addition. There's something special about them, and we'll talk about them. That'll be next time. So see you tomorrow if you're in lab. Otherwise, have a good week till Wednesday.